we present PICO, a new method for joint reconstruction of humans and objects in 3D from in-the-wild images. Humans routinely interact with everyday objects. We ride a bicycle, brush our teeth, eat a banana, carry a surfboard. Thus, recovering human-object interaction, HOI, in 3D from natural images is important for human-centric applications, such as smart homes, mixed reality, or assistive robots. This is challenging as humans and objects come in a variety of shapes and sizes. They mutually occlude each other, and their contact is often ambiguous in 2D images due to depth ambiguities. Consequently, existing methods focus on controlled settings such as in-lab datasets with known object shapes or contact, tackle only limited object classes, and often struggle in the wild images. To address this in this work, given an arbitrary in-the-wild image such as a man sitting on top of an armchair, our method, PICO, estimates human pose and shape, object pose and shape, and their spatial arrangement and contact correspondences, all in 3D. PICO works on diverse and challenging human-object interactions in arbitrary in-the-wild images, such as the ones shown here. Note that PICO successfully recovers several previously untackled object classes. To this end, we make two contributions. First, we collect PICO-DB, a unique dataset that pairs natural images with dense vertex-level 3D contact annotations for both the human and the object, as well as rich 3D contact correspondences between them. Here we show example annotations from PICO-DB. The RGB image is on the left, the color-coded body contact is in the middle, and the annotated object contact on the right. To collect PICO-DB, given an RGB image, we retrieve the matching 3D object from the Objaverse dataset by querying the closest object embedding in the joint image object latent space of the OpenShape Foundation model. Then we leverage the body contact annotations from the Daemon dataset and design a novel method to project the body-only contact annotations onto the object mesh with minimal human effort. We divide Daemon's full-body contacts into neighboring vertex patches, recovering one patch per contacting body part. Each contact patch is parameterized with a contact axis, which is a geodesic open curve on the patch surface. Since every patch vertex can be fully parameterized with its contact axis, transferring body contact patches onto an object boils down to transferring its axis. This requires just 2 clicks, one for the axis start location and one for its direction. We scale this approach for PICO-DB by crowdsourcing contact annotations via Amazon Mechanical Turk, using a custom-made interactive software tool. Second, we leverage the PICO-DB dataset for building PICO-Fit, an optimization-based method that fits 3-dimensional body and object meshes to an image, guided by rich contact constraints. Our key insight is to leverage 3D contact on the human, which is easier to estimate as a key to query the corresponding object contact from PICO-DB. We first initialize 3D body pose and shape via the off-the-shelf OSX model, and the object shape via the OpenShape-based database retrieval from Objaverse. Next, given an unlabeled image, we automatically infer 3D body contacts using DECO. Based on these, we retrieve from PICO-DB the nearest neighbor body contacts and the respective object shape, object contact, and body-object contact correspondences. Finally, we use the recovered contact correspondences in a 3-stage fitting approach. In Stage 1, we recover the object pose by keeping the human fixed and registering the object to the body by minimizing the contact loss between the contact correspondences. However, all body regressors are imperfect and inferred bodies can be noisy, resulting in misalignment when projecting the human and the object onto the image. Thus, in Stage 2, we align the object to the image, using a mixture of image-based and 3D losses. And then in Stage 3, we optimize human pose by fine-tuning the limbs of the human that are in contact with the object, considering the contact information, image alignment, and mesh interpenetration. We demonstrate our simple approach to be surprisingly effective. We quantitatively evaluate PICO-Fit on the unseen intercap dataset, and we find that our method significantly outperforms all baselines, both with and without ground truth contact data. We also evaluate PICO fit against state-of-the-art methods on in-the-wild images through a perceptual study conducted on Amazon Mechanical Turk. On average, participants deem reconstructions produced by PICO fit to be more realistic over baselines 75% of the time. Qualitatively, PICO fit results in more realistic reconstructions compared to state-of-the-art methods. Look closely at the contacting body parts of the human. Here are a few more examples that show how our method can find well-matching object meshes and reconstruct nuanced human-object contact, even for unusual interactions. These results show that both PICO-DB and PICO-FIT can be useful for the computer vision community. Our code and data are available for research purposes. For more details, please visit our poster and website. Thank you.